that people can take a look at. Next we have Angele. You saw who she was from the movie. She's going to go into a little bit about what she found out from, Thailand, and then also kind of talk about corrosion more generally, and then answer some questions. So please welcome Angele.
You can see what you're going to do. Have you been? No. Well, I mean, you were there.
So I'm going to jump right into the NCC of Thailand story. First, I want to thank the Access Fund for having me here. I really enjoyed working on this project, and I'm excited to talk about it because it's on metallurgy. And I just want to thank all the people here who worked so hard to put in the safe bolts, because as a climber, especially spending time in El Cab, I always appreciate it when the bolt is a good one. So thanks everyone here. So full disclosure, I've never actually been to Thailand. I get jealous hanging around these titanium guys, but I got involved about 4 years ago. Actually it was about 4 or 5 years ago. When Greg Barnes from the American Safe Climbing Association, he dropped off a hanger, Petzl hanger, that had just, broken like a potato chip in his hand. That was from Raleigh Beach, is that right?
Yeah.
Yeah, it was from Raleigh Beach.
I just clipped it with a quick draw and twisted.
Yeah, twisted.
It looked so bad that at first I clipped it with a quick draw, placed the nut, clipped the nut, then
Yeah.
I just...
Yeah. So he came by where I worked. I worked for many years for a very large consulting firm. We did a lot of metallurgy, did a lot of basic product failures, plastics failures, metallurgy failures, and for all sorts of industry. A lot of automobiles, pipelines, medical devices, and electronics. So we had the facilities to take a look at this. Now, I had heard about, corrosion in Thailand, but you hear everything, right? And so I just didn't really think much of it. But I took this fragment and, started looking at it under a microscope, and it was just, to a metallurgist, it was a total SCC horror show. I mean, I've never seen SCC that bad, and I've spent years looking at SCC in pipelines, and I've seen SCC, but this was just incredible. It was incredible. And I didn't know, I'll give you the SCC story, and I'll tell you that again, but I'm certainly not the first to call it SCC. John Burns and Mike Shelton from Colorado, they called it SCC, and I'm sure there's a bunch of European metallurgists who call this SCC. And I'll tell you that again, but I think what's more important to me, and more important for us, is to understand why. Because it's just not obvious why it's so severe and happens so quickly in Thailand. So here's the basic scheme of the talk. I'm gonna do the best job I can. Just a few slides. I'll introduce stainless steels in general. I'll introduce the different kinds of corrosion, because SCC is just one type of corrosion. It's the most severe, or the kind that would scare you the most. There's actually more than one type, certainly more than 2 types. And then before I go into the SCC in Thailand, I don't want to completely malign, the 316 material, because it's really good material. So I want to talk about what the resistance is for this material. It's a good one. And then I'll tell you the SCC story again. And then there's another case study I do want to talk about, because I know with the legal stuff this morning, it was important to talk about precedents, and is there any legal precedent for suing somebody over this kind of thing? Well, metallurgists think the same way. It's just that we need technical precedents. So when I look at this, I can't, we can't, as metallurgists, especially working for that firm, just say it's SCC in a coastal environment. So who knew? you can't say that. You have to say, well, why did it happen? You know, and what were the conditions that caused it? Because it's not obvious it should have it should have happened in the first place. And then I'll talk a little about titanium and other materials. So I'm supposed to. I have pretty strict marching orders that I'm supposed to cover all this material, but never sound like a geek. I don't know if I'll succeed though. I'll certainly try my hardest. So here's just a stainless steels. We talk about it like it's one material. There's like maybe 150. I mean, I don't even know. There's so many stainless steels out there, and you know, people use them for all different reasons, and they have, you know, wish lists or criteria for using each particular one. But basically, you know, what makes a stainless steel versus not a stainless steel is you have to have at least 12% chromium to get that, you know, to get that grade. And so what does a chromium do for you? Well, steel corrodes, and so what happens is a chromium also sees the oxygen in the air, and it forms a chromium oxide, which is a very thin layer, and that protects the underlying steel from further corrosion. 12% chromium isn't super stainless, so that's just kind of minimally stainless steel. You can easily get to 20%, you know, in high 20s for stainless steels. So here's just sort of the classes of stainless steel. There's, you know, 5 classes. I like to think of the steels being in 3 sort of phases of steels. There's the austenitics, there's the ferritics, and there's the martensitic. So the stainless steel that I'm going to be talking about is the one at the top. It's the austenitic one, 316 Petzl. You know it's austenitic if it's not that magnetic. All the other steels are magnetic. The duplex is a hybrid of austenitic and ferritic, and the precipitation hardening steel, that's also a martensitic steel, but it has little microprecipitates in it that give you better properties, including corrosion resistance. So here's like a really complicated tree. I don't mean to like make you miserable, but I want you to appreciate the complexity of stainless steels. So you start in the middle, you got 304, that's like, you know, real standard stainless steel. So there you have 19% chromium, about 10% nickel. So we're going to be down, you go down into the left, 316L, so that's, you just added some more molybdenum, we call it moly. And you basically, it helps you with additional pitting resistance. And then you've got lower carbon, that's what the L stands for, so 316L. That gives you the properties. And so you can see, like, you have your supers, ferritic stainless steels top left, martensitics are down right. You know, use those a lot for your nice steels. Surgical instruments, they like to use those. Your ferritics, your appliances in your kitchen, those are going to be your ferritic steels. It goes on and on. Generally, there's no free lunch. So if you move around on this diagram, you usually give up something to go to something else. So if you want better corrosion resistance, then you're going to give something else up. But, you know, you want machinability and corrosion resistance, well, you know, those are kind of competing interests. Weldability is another one people want. People want super, you know, high toughness. They want great, you know, great toughness in all sorts of temperatures. So anyway, that's just kind of a complicated family diagram, but that'll kind of give you a sense of how large stainless steel is. So when people say stainless, I'm always wondering which one. For me, I'm always going to be talking about 316 because that's a Petzl hanger that I looked at. So for the corrosion types, these are just a partial list, but these are probably the ones that are most relevant to climbers. So the top one is general corrosion. So general corrosion is kind of like the nice type, but if, you know, what you hope is when you put a material out there and you know it's corrosion resistant, it doesn't mean it doesn't corrode. It means it corrodes at a much lower rate than regular old steel, or steel has a corrosion rate as well. And you hope that your wall thinning is happening at the rate that you expect it to have. And you hope that after so many decades of service, you're going to pull it out and put it in, and you hope that's all predictable. So general corrosion is kind of the nice kind because it's predictable. You know, you should know what's going on, and you're not getting, you know, big notches in there that are going to concentrate stress and make you fail at a much lower load. Your pitting corrosion, this is actually really common with stainless steels. So basically, it's kind of like a local corrosion effect where I won't get too into it, but you get basically shallow. You can get shallow pits, you can get kind of deep craters, but this is caused by chloride ions, so salts, and they were able to set up like local concentrations and give you pitting corrosion. I probably do a lot more pitting corrosion type work than anything else. Then there's the galvanic corrosion. So galvanic corrosion is when you would pair two dissimilar metals and give it an electrolyte, or water with a little, something dissolved in it. Could be salts, could be the organic acids that you get from nature, any of those things. When you do that, basically one metal becomes, you know, the cathode, one becomes the anode. The anode is going to oxidize. And you basically create a driving force. You are going to drive corrosion in one of the two metals, the one that is less noble, the one that is active. The one that is noble will not corrode. So you have all these galvanic pairs, and when you pair them and give it an electrolyte, you will have something, you know, you'll have a galvanic reaction or galvanic corrosion. How fast that occurs, it depends what you're pairing. It also depends, like if you're going to pair, if you make the part that's not corroding, if you make that really, really big, and you make the part that is corroding really, really small, that's going to happen. You know, you're going to lose your part in thickness very, very quickly. So one thing about galvanic corrosion is you asked what were the materials that were paired, how often did it see an electrolyte, and what was the geometry difference, and how fast can that reaction occur. So those are the kinds of things you see, but you really drive corrosion. And of course for climbers, steel and aluminum would be the big one. You put aluminum with steel. Aluminum is going to corrode. Aluminum can protect itself very, very well with its own oxide layer. That's why aluminum does well. But when it sees steel, it loses the galvanic battle. So steel will drive the corrosion in aluminum. If you pair two different steels, if you pair stainless steel with regular steel, well, guess what? Now the steel is really going to lose. And you're going to drive the corrosion in the steel. And that's really important. And you'll know it when you see it, because you'll see one component is corroding, the other one isn't. That's probably galvanic. Crevice corrosion, I haven't seen this in climbing, but I would think it would occur sometimes. This is where you have basically a stagnant area of, people in the marine world worry about this, where you would have like a bolt head, and the lip of the bolt is not seeing as much air. So if you have stagnant air with the same material that has a lot of air around it, you can drive corrosion in that stagnant area. So people who install bolts, they try and make things really flush to prevent corrosion from occurring. And then stress corrosion cracking, that's the worst one of all, because it's very insidious. If you're lucky, you see corrosion. You'll see corrosion product, but you don't have to see corrosion product, because it can happen deep down there. And basically what you get is really, really fine, highly branched cracks. And it's quite terrifying, because this can fail at a very, very low load. And the crack keeps getting driven in deeper and deeper into the material, and it's highly branched. So pipeline companies worry a lot about this. And if you find just a little bit of stress corrosion cracking, they'll pull out hundreds and hundreds of feet of pipe, shut the whole pipeline down, and it's a big deal. Regulators, and if anyone ever actually gets hurt, it's any of these corrosions with product failure in normal industries can result in loss of property. If it's loss of life, you've got a team of attorneys and suing each other and regulators. So all of this kind of stuff can be kind of a big deal. So stress corrosion cracking, this will be the 101. So I told you, so you need a material that's susceptible to stress corrosion cracking in the first place. Things like titanium grade 2 in certain corrosive environments like the one in Thailand, it's just not going to happen. But with the stainless steel, the 316, if it sees chloride ions above a certain level, and there's enough stress in the material where there's some sort of a tensile stress with the pencil hanger, it had been cold worked and there was a bend in it, because there's bends in all hangers. So if you see there's a tensile stress above a threshold, a certain threshold, in a corrosive environment, then that sort of combination of factors will give you stress corrosion cracking. Okay, so I want to really make sure, though, that when I say chloride ions, you say that and you can see chloride ions everywhere, and people assume that stainless steels fall apart every time they see salts or you cook with them, and that's not true at all. They can handle a lot. It's just you can't. If you're going to do that, you can't, stress your material and then give it a huge amount of salts and expect it to last forever. That, then starts to fail. All right. So I do want to give sort of a stick up for 316 a little bit before I malign it in the Thailand talk. Because one thing I found when I talk about the Thailand thing, that people start freaking out about 316 in general. So I want to tell you what industry tests people use to qualify 316 and how well it does. So I'll talk about seaside and then getting really aggressive with boiling the stuff in certain chloride salts. And then the chloride films, which is really important for climbing bolts, because when you think about it, you know, it's really it's really corroding in the atmosphere. So you're thinking about forming thin films of something corrosive on the surface of your material. So anyway, this is the kind of test that people do in general for their material. You'll see civil engineers do this a lot. They'll put a test coupon of their material in the environment that they're worried about, and they'll monitor the coupon more easily. So people did this for 316, and they did this for up to 15 years duration and tested it for SEC. And this is a widely publicized study, so it's in a lot of engineering textbooks, and it governed engineering for quite a while. And basically what they saw is they didn't see any 316 failure in this coastal marine environment. And so that qualified 316 for marine use, and that's why that's why it's used, and it's still used, and it does well on ships. But this is kind of like a lot of the engineering that was behind it. So you'll find that the traditional engineering viewpoint, that's in the red below, is that SEC does not occur in these stainless steels below 140 degrees Fahrenheit. And the engineers over 60 degrees C, if you have neutral chloride solutions. So the engineers that wrote that, they thought they were being conservative. They actually thought it was safe up to 100 degrees C. So, but there's one sort of caveat to that. If the material is sensitized, and I'll talk about that, then you will see it. But if you don't have sensitized material, then you're not going to see it. So here's something else that they do with 316 that it can handle. You can put it in boiling salts, 26% sodium chloride, and you can stress the heck out of it by making a U-bend. And you'll find that it can handle, you don't see any cracking after 30 weeks. Now keep in mind, sea salt, like seawater, is only 3.5%. It's mostly sodium chloride. So this is really aggressive. This is like 7 or 8 times more concentrated than seawater. You stress the heck out of 316, and it lasts 30 weeks in this boiling, cauldron. But make it a little worse. Drop the pH down so you're boiling in vinegar with 26% sodium chloride in the U-bend, and now you're going to start to see some cracking. But I just want you to appreciate how aggressive you have to get before you start seeing SEC, and look how quickly they were seeing SEC in Thailand. It's amazing to me. It really is, because sea salt is mostly sodium chloride. Okay, here's an even more aggressive test that they use in industry when they know it's, their service conditions are really bad. Nobody has time for coupon tests in 15 years. So they boil the bejesus out of their material and see if it lasts. So it's called the ASTM G36, and instead of using sodium chloride, they use magnesium chloride. It's substantially more aggressive than sodium chloride. And the temperature, they can do it at 43%, 155 degrees C. So that's what I did. I took a pencil hanger and I put it in there and I boiled it, and it cracked very quickly, cracked 4.5 hours. And then I did it again, except instead of using 43% and 155 degrees C, I went a little down in temperature, 35% and salt, 35% salt, 125 degrees, and then it took me 26 hours. Actually, I'm saying less than 26. I was working, so I didn't have time to check every half hour, but it was under 26 hours.
Is there a way to simulate the boiling times with actual longevity times? Is there some kind of comparison that you used?
Yeah, there is. Yeah, I mean, people are always leery of saying if it can survive X amount of hours and extrapolating it out to years. Everyone wants to do that, and right. I always kind of like back away from that. Yeah. But no, that's a really good question, which brings me to my next slide. Okay. So here's what industry would use, and so time to failure. That's what we care about. And on the x-axis, I put nickel. And I didn't tell you why I put nickel yet, but nickel is a common alloy in stainless steels. And it's just so happened that the 316, or that austenitic class, has quite a lot of nickel in it. And you can see, in fact, it has about 10% nickel. So you can see around 10% nickel. The time to failure is really short for that class of steels. And you can see if you go way down in nickel content, so you go to your ferritics or some of the duplexes, you get a lot more time in that bath. Or in that boiling magnesium chloride. If you go up a really high nickel, well, your cost is also going to go way up because nickel's expensive. But at that point, you're going to also get a lot more time. based on what I've seen in Thailand and how severely corrosive it is, I would want a material, any material that someone uses out there to, to survive 1,000 hours in that test, given, for Thailand at least. Okay, so I got one more test to do, and I know you want me to get to the point, which is about, this is about the point where, like, people say, just get to it. But I got one more test, and you got to listen to this one. Stay awake for this one. This is out of Japan, and so I've been talking about boiling the stuff. They had a much more practical way of looking at this. They know that, what we're really talking about with these steels and atmospheric corrosion is that you have some thin film, and you got to wave your hands a lot when you talk about this. Some thin film that with some salt. And then you have high humidity where you have a more dilute film, that would be the one on the left. You have low humidity where you're going to dry that out and you're going to get a really concentrated film, more corrosive. And at a certain point, it's going to be so dry that you're just going to have solids and you don't have to worry about corrosion at all. So what the Japanese did is they did a really nice study where they took 304 and 316 and they stressed the heck out of them with a U-bend specimen. And they put different salts on there. So they put, the sodium chloride, mostly sea salt, magnesium chloride, calcium chloride, and zinc chloride. And they just said, can films of chloride salts crack these steels? And the answer that they got was, not sodium chloride. Magnesium and calcium and zinc chloride salts can do it, okay? So you can see where this is going to lead, right? All right, but it gets technical. This is my technical geek slide, and you have to listen to this. What they found was, and they said, you don't have to worry about this, because even though magnesium and calcium and zinc can do this, they require very low humidities in order to get that maximum concentration. So basically, each salt you can only get so concentrated before the solution can't handle anymore. The most concentrated you can get with sodium chloride is like 16%. And in order to get that number, you really need like a magical humidity of 75%. Well, with your other ones, with magnesium chloride, you can get much higher chloride, but you need a really low humidity. So basically what the Japanese said was, yes, these salts are very aggressive, but you don't need to worry about it because it's unusual to have such low humidity in coastal environments. So we don't have to worry too much about that test. Anyhow, let me get to the SEC story. Okay, so this is what I received from Greg Barnes. It was a small, actually I did a cut on the right, but it was just a fragment of a Petzl hanger, and he installed it it was installed in '94, and it broke in 2004, tested by hand. So I did chemistry and a hardness on an intact hanger. This thing was so damaged I couldn't do that on that. And confirmed, yeah, it's 3.6, that's the chemistry, so you can see it's got 16.5 chromium, 10 nickel, and some moly. And it came back 316L, and then the hardness came back much harder than an annealed 316L material. So that just means Petzl is cold working it. There's nothing wrong with that. They're getting their strength up. And that's it there. So I put this under a microscope, and it's just, what you're looking at is just a fraction of the hanger and has cracks going everywhere, fine cracks going everywhere. And it was just, it's over the entire hanger cross-section. I've never seen stress corrosion this bad. Like a pipeline would get excited about like one tiny little crack that goes a third of the way down that micrograph would freak out a pipeline company. So it was pretty incredible to see this. And here is basically what they do. You call it etching the microstructure. So now you can see the grains, your austenite grains in this steel. And basically what you're seeing is a crack going right through those grains. So there are probably a couple of metallurgist geeks in the audience. If this was a huge litigation product failure company, I would go on and on about this because it means that the crack went through the grains instead of around them. And if the crack had gone around them, it would have said there was something wrong with the Petzl hanger. Basically, it sensitized that material, and when they were processing it was processing correctly. That's not the case. So there's nothing wrong with this material, and yet it was still SEC. So that was kind of a big deal. Because at this point, I don't know why it's occurring in Thailand. It really shouldn't be happening. So then what we did is we took the fragment, the original fragment, they go back up, and we opened it up to give fresh crack. So, because I wanted to see what kind of corrosion product was inside. So we opened up a fresh crack, and we did a chemical analysis on the inside. And we saw, of course, when you see corrosion products, we saw, iron and oxygen and nickel, and we saw chloride, which you would expect. It's up against the ocean. But what we quickly saw was that the sodium-calcium and the sodium-magnesium ratios were not the typical signature of sea salt. If you look at sea salt is mostly sodium chloride, and then you have some magnesium and calcium, and you look at the ratios, and you should have like 25:1 sodium to calcium in sea salt. You should have like 8:1 sodium to magnesium ratio. And we were getting like 1:1 and 1 to 6.4. So there's a lot of calcium and a lot of magnesium in this hanger. Who cares? Well, what's the study I showed you that shows that that's kind of important? Yeah, the Japanese study. But we're on a coast, so it should be really high humidity. Shouldn't be a big deal, right? So this is what I got from a geologist. I don't know anything about geology, so I had to kind of figure out what was going on with the geology out there. And this is going to be very obvious to people who have studied geology. It wasn't obvious to me. But that the limestone, the geologists call that tower karst. And in the tropics, it undergoes what's called tropical erosion. And so what you get is those incredibly dramatic features, those stalactites and the sort of the caves that come out of that. And the reason is that the lush vegetation that they have in the tropics gives you much more acid in your runoff. And so that's able to dissolve your limestone much, much more than limestone in Wyoming or Colorado. So plain old rainwater weathers limestone for sure, and it also dissolves limestone, but it's nothing as dramatic as what tropical tower karst gives you. And so you also have this hot tropical sun. So basically what you have is this acid water. It dissolves your limestone. You're getting that calcium and magnesium salts mixed in with you get your chloride from your ocean, and you're mixed in. And then you bake off the sun, you bake it off. And so the limestone's constantly going through this dissolution, and then it turns into solid again, pre-precipitation, then it dissolves, and then it reprecipitates. And you go back and forth, and that's how you get this really cool stuff. Well, your hanger's on that stuff. And so you have this acid chloride dripping all over your hangers. And so it's a big deal. It's no longer just plain old marine environment. It's plain old marine with acid chloride dripping all over your hangers. Okay, so I need to switch to that other case study I talked to you about, because this is a case study. This is an indoor swimming pool where they use an austenitic stainless steel 304 instead of 316, very similar materials. And they use this material in rods, rods under tension, to hold up their roof. And what happened is the roofs collapsed in 1985 and 12 people were killed. So you have this huge product liability, and lawyers, it's a big deal when there's loss of human life from a product failure or construction material. So they did a similar analysis. They said, yep, it's SCC, it's transparent, the crack goes through the grains, not around the grains, nothing wrong with the material. They did the same thing we did years ago. And the same thing is that this material should not have failed. You can use this material in the swimming pools, and you do. You use it all over swimming pools, and it doesn't fail. So they had a really expensive study on their hands where they had to figure out how it did. And basically, I'm going to cut to the chase, but they found that they had really high levels of magnesium and zinc that they think they picked up from construction materials, and they had high levels of chloride. Okay, the high levels of chloride, I'm not going to bore you with the details, but there's like thick papers where they had to figure out how pool water that has chlorine gave you chloride up top. But basically, when you urinate in a pool, you form chloramines, which are still not corrosive. And they go up into the roof, and that degrades to acid. And so they had to work really hard to get that. But they figured out that the aerosols in the pool atmosphere degraded to acid chloride. So they also figured that some of their construction materials were giving those calciums, magnesium and zinc. And then they have an artificial environment where they basically create a lot of aerosols because they had fountains, and they keep their humidity quite low because it's an indoor swimming pool. So they had sort of this witch's brew of conditions that gave something that was aggressive enough to see this type of stress corrosion cracking in the 304. So I'm trying to make this simple here, but basically these are all the conditions that lined up on the top for the indoor swimming pool roof collapse. And so they had the 304 under tension, I'm going blue boxes left to right here on the top. So 304 under tension. They had chloride from that complicated chemistry that gives you chloride. They had magnesium and zinc from construction materials. They had acid because that was part of the decomposition. And they had an artificial low humidity situation, which is matched, again, they were looking for precedent too, which matched what the Japanese told them, which was, if you have a situation where you have low humidity and these salts and acid and this material under tension, you can get stress corrosion cracking. And so, and then they published a ton of stuff because, they had to, because Europe was changing their regulations on this. So I'm buried in these papers, and they keep saying, you don't have to worry about this because coastal areas are very humid. So you're not going to get this witch's brew of conditions happening in coastal areas. And so I went through and, what do we have? Well, we don't have low humidity, but we do have a cold work 316 material. We have chloride for sure from the ocean. We have calcium and magnesium that are leaching from the rock. Any geologist will say, duh, to that. It was not obvious to me. We have acid, which is how you get the dissolved calcium and magnesium in the first place. But the low humidity really stumped me. I just couldn't get over that. And I didn't feel comfortable reporting my findings to the metallurgical community because they would have said there's no precedence for that. And then I finally looked at the weather in Thailand. So I was like, and sure enough, it's humid. But if you look at the high humidity, it's almost always 100%. Sometimes you get some 95s in there or some 92s. But they have a low humidity as well. And if you go to a really good weather station, I went to Weather Underground, but you can go, especially around this time of year in Thailand, what happens is you do see some really lows around the 40 to 60%, which is the level of humidity that they saw in the indoor roof collapse. And so basically we have humidity, and it's usually humid, but there are enough intervals of low humidity where you can get those high concentrations where it is aggressive enough. You get the acid and the concentrated acid, calcium and magnesium chloride solutions. And then that certainly fits the precedence for, it certainly fits the Japanese study, and it certainly fits the European study as well. So this is a long song and dance, but I kind of had to go through these in order to understand how the why part of SCC, the SCC is easy, the why is a different thing. So what we did is, this isn't really of interest to climbers, because climbers, it's obvious it's happening, that's all you need to know, but the metallurgists actually need to be told this. So we published this in a metallurgical journal, and it was a journey, but in a journal, and said that this is failing, like chloride, SCC. Acidic soil waters are dissolving the limestone as usual, but they're creating these very aggressive salts. But I think that the real part for the metallurgists to learn was, guess what? Coastal environments can have intervals of low humidity that are bad enough to cause this corrosion. And that was kind of the news for the metallurgists in this. So I want to talk just real briefly about the titanium replacement anchor. So there's titanium there's a couple of different grades. Mostly when people are talking about titanium, they're talking about the grade 2 or the Metallurgy Bolts, or this is considered an unalloyed titanium. This is a great material. It's absolutely fantastic. It's immune to chloride attack at any stress level. There is no threshold stress above which this material stress undergoes SCC. So personally, I boiled the stuff in that for 28 days in the magnesium chloride, and I never saw any cracking, including the weld area. It can withstand hydrochloric acid to high concentrations. It's a tough material and it's weldable. There's also, the Thai 6-4 is another alloy that's out there. I don't know if it's really being used for this type of material, but these materials differ in strength and they also differ in corrosion resistance. And I can talk more titanium and also mechanical testing, but I think Steve Gladue, who's done, where's Steve? Oh yeah, he's done a lot more of the testing, mechanical testing on these materials, and I think that's really important.